You can go ahead and click on the paper. What I thought we'd do today is just go through, there's a ton of really cool visualizations that this paper had. So what I thought was we'd go through, maybe first start there so we can all build up some excitement about how cool this paper's work was. And then we can jump in and kind of go through the paper and kind of what was the implementation behind the paper. So first things first, this is DragGAN. This was kind of the first time that they brought together interactive, point-based, so being able to actually interact with the GANs and manipulate the image, which was kind of like the novel concept behind it. What I thought we'd do is just start with some videos so you guys can all see what's possible. So let me pull up here. Let's see the main demo first. So this is one where they're manipulating an image of a dog. The red points here are kind of what they're calling the handle points. So it's where it starts. And then they're moving it, so you can see with the ears, they're moving it towards the blue points. So you're giving kind of, you're starting with the handle point, you're moving it towards your target points. And we'll compare kind of a couple of examples where they do DragGAN's paper versus a previous paper, and just all of these things that they actually opened up its jaw, showed the teeth. And so like in this example here, you'll notice this was over to this target point here, and you'll notice that the setting behind is also getting adjusted properly. This is just a fun one to watch. This is one. And so they've tried this on animals, a diverse set of animals. They've done this for humans. They've done this for landscapes. And it's actually kind of interesting just how rich the feature space behind this was that the model was able to use to actually track next positions and get it right. Like you move the lips over, okay, the teeth should show. Like it just knew to kind of do that, which is really, really cool. And this, what they're doing here is they're drawing a mask. So they only want manipulations to be in that certain region. So let's take a look at these. Yeah, that's pretty dang cool.
And I'll drop a note. It's pretty amazing that like when it extends the dress, it understands the folds, understands gravity, or maybe not gravity, but understands how it should look as you extend it. Like there's so much structure it's understood about the thing you're moving from just a picture that I think surprised a lot of us in like what you could actually do with this.
Yeah, and maybe let's just start there actually. Like for example, oh, there's a really good image. So they were comparing, this was the input, this was the target, and in this input here, the red points are again all of your handle points. The blue points are where you want kind of your target points, maps the target points. And then this is kind of call it a benchmark. This is kind of the most comparable thing in the past, user controllable LT, name of another approach. And here it moved the parts of the face, but it didn't highlight the teeth, which was there in the target. And so just to give you an example of like, even with the manipulations that the user wants, it's still able to kind of more realistically produce more realistic images of what actually would have happened if you had dragged it, which is really, really phenomenal, actually.
Yeah, and I think that's it's a fascinating one when you think about like what must be understood by the latent structure, because what you're doing is you're updating what we'll talk about in a bit, but you're updating the latent structure that's generating this by moving the latent structure a little bit. And the fact that, and by latent structure, it's kind of what the model knows about this face. Well, it knows there should be teeth near the lips, because when you move the lips away, generate the teeth. So like, there's just I think we're really, really impressed by like what does it show? Like, it shows how much is in latent space and known, and what by moving and manipulating those embeddings in latent space, like what it can actually do in the picture, what it can do by way of, I guess, the model it has for the person it's rendering.
Yep. Cool. Well, Jason, what I thought we could do is maybe just start with, we could start with a little bit of like, what was there in the past, kind of like just walk down the paper. What was there in the past, kind of what was the novelty and the method that this one approached, and then we can jump into some of the, just kind of follow the flow of the paper. I don't know if you wanted to, if you wanted to show there's a lot of really cool experiments with this one. So I don't know if you want to spend a little bit more time just on the experiments first.
Yeah, let's do a couple more. Like I think the lion's, generating its teeth, or yeah, I think some of those are pretty amazing as well. But I think we can start at the beginning. And I mean, the older methods to me felt very rough in control. So you could do something, you can in paint, you can change something, but grabbing physically something in the image and moving it, I mean, that feels completely unique in the set here. Where, I mean, it's just amazing. So I think the previous, and when you talk about it, there's kind of two things they talk about, which is in the previous kind of ways of doing things, there's two big problems in this. I took away. One was knowing first how to edit the latent space, but then since you're doing it in small increments, you've also got to like follow your point. So there's another challenge of point tracking, making sure the point you then grab to do the next movement, next small movement, matches the physical object's point where it is, where you moved it to. So there's kind of like two major problems being solved in the paper. One is that like movement of the embedding, and the other one was like finding the point on the object in the new space, in the incremental space you've created. So there's kind of two different problems they were solving, and they called it, and to be honest, I had never heard of the point tracking one before. It's pretty
so this, what they're doing is drawing the mask. So they're saying only have the manipulations within the face, so not the rest of the image. So I'll keep playing here, but you'll see it only sticks to manipulations there. That's kind of cool. They're doing, yeah, open the mouth.
Yeah, it's amazing. I think for me, it's amazing, again, what the this is all being manipulating the embedding, and like what else, part of it just paints a picture of like what else could you do if you knew what the embedding meant, like what other manipulations of the picture could you do, and then versus just translations or movements. You want to go to the paper?
Yeah, I could pull up a couple other ones. Yeah.
More.
Okay. Yeah, I can go into the paper. Okay. I just feel like these are so cool to watch. I'll send this link.
Yeah, go ahead.
Like these are, once you start watching this, it's actually kind of cool what it's learning. Like how much it has to know in order to, about the embedding space or the feature space to really do this properly.
And you notice how the
Um,
fold came down, if you see that, like it like knew the fold was there and extended it.
yeah,
Like you're kind of knowing like if you look at the right arm there, how it kind of knows the fold should extend.
yeah,
And it's just physical structure that exists in the real world is taught, is not so obvious in a picture when you just look at the pixels. But the point I think with this is it's trained on so many images. It understands some of the physical things that we would know ourselves naturally.
yeah. I'll just do one last one, then we can hop into the paper. But this is one with landscapes. I thought this one was really cool because it understood shadows, which
Mm.
you look at just what, moved the water down and like it extended the shadows and the images above. There's a couple here where they add in, or it's like moving from sunlight to sunrise or things like that. It has to know what's normal, what's possible. Okay, I don't know if
Oh,
anyone
the
else is
shadow. I
as
mean, that's
fascinated
pretty
with this as I
amazing.
am right now. This is really cool, right? Like as the trees grow, the shadows are increasing.
Yeah.
Um, so there's so much that it just has to know. This is a good one.
Yeah, and Harrison's question is there a sense you think that this model also has a model of the world? I feel like I mean it's a good question. I mean, I think there's I don't know if you see Jan LeCun, he's kind of like big on the world big on the LLMs aren't a world model stance, which in the world model idea is I think originally comes up a lot in the original RL thing, but I think I don't know, my take is it definitely models portions of the world. I think the world model, like, is it a true world model, feels like a very high level debate that's going on with people that are probably more have many more years than me, that like I would I don't know, I feel like I should defer to, but it definitely has some model of the world. I just don't know if it's exactly what, does it have enough information about, has it been through enough experiences? Like think of all the things we've seen, how many days we've seen gravity go down or things fold, or the way a dress falls. Like we've just seen a lot of those, and the question is like how much at some point you've got this model of things that you quote unquote think is true, and I think it's built some model of things enough to be able to move things around. I don't know if you probably would say it's got like human level model of the world, probably not. But it's got enough to do quite a lot. I think more than most people would say. But it's a good question.
Yeah, yeah, that is. All right, let's jump into the
Yeah.
paper. But definitely watch some of those. They're very, very interesting. So maybe we could start with like, okay, what was novel about this paper? And what was kind of previous in the past, what existed before this paper existed. So they kind of broke up the world of GANs into a couple here. First is really, call it unconditional GANs, like style GAN and style GAN 2, where you can't really edit the actual images. So you know, so there's these, can't really take in human input and manipulate. There's in the past kind of these, broke them up into these conditional GANs where the user receives some kind of, call it segmentation map, and asks it to actually generate photorealistic images. And I think there's another one that they were talking about here, which is kind of like, well, you can take semantics from like one sample. It's almost like style transfer, where you're taking semantics from one image applied over to another image. and then what's kind of the new image that's created. But this was really, I think one of the key points of this paper was that this was really one of the first times that that users can give a handle point, can give a target point, and then it really, you can manipulate the actual image using just these two inputs, which is kind of, just from a method perspective, how does it work? Anything else you wanted to add there, Jason?
Yeah, I think that was great. I mean, I think it's fairly unique in its ability to like tightly control what you want it to do. Grab a point in the space and move it like that feels very 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 novel, and then I think the approach they did is pretty novel too in terms of the technique.
Yeah, and so they right here were the first to connect the point-based editing problem to the intuition of discriminative GAN features and design a concrete method. So that was kind of what was unique about this paper. And what it does is, as you dive in to the actual method, it breaks it up into a component of point-based manipulation and then a component around motion supervision. So what does that actually mean? So first is the point-based manipulation. So in this case over here, there's kind of the handle point, there's the target point, and I think the part that was interesting was that for me at least, the point that was interesting was that every time you saw an adjustment in it does a first step, it readjusts. The question's like, well, where does the new handle point now get placed? And that was something that the team behind the paper, actually, I think there was a lot of detail in the paper about, well, you manipulated the image and they actually used the feature space in the new kind of image that was created to come up with the new handle point. And that was really novel, because then each step you're kind of editing that handle point to move towards the target point. But that we'll dive into that. They go into depth during the method section, but every single step here is basically updating, each iteration's updating where that red point is as it moves closer and closer to the blue point.
Yep.
Good.
And so that's my take as well, that if you go up there, there's like the two steps, which are like the motion supervision, which kind of moves W to W prime, and there's point tracking, which gets moves your handle to the right spot, and then you kind of move it again and do the same thing over and over again. And then the magic of the W to W prime was probably the next section.
Yep. That was in, yep.
And,
go ahead.
Yeah, and I was gonna say, like, this is like, I feel like lots of papers you start to get like to the heavy math section. My take of this was it took me a couple reads. I mean, it took me a couple reads, but what it looks like is there's something called a feature map, which typically is like an activation, is typically a 2D map in an image model that is like, you can see it there in P, the square. It's typically a 2D map, which is based upon which is an activation of pixels based upon trained on data. It's like normally it's a map based upon like activations in the real image. My understanding was there's basically if you were to move the map slightly towards T, which is what they create a vector D that's in that direction. You look at like the difference between the two maps, and that difference is that if below is so F at that point, if they look at the feature map at the current point you're on, the feature map and a slightly movement in the direction you're going, look at the difference between those two, which is the loss function below. And then the magic is once you have that loss function, you create a gradient. So you back propagate that loss through the network. they lose one term there. So it's only, they only hold the one term. That's the, if you, they mentioned below, they only hold the movement term as they calculate the gradient. And then the gradient gives you the update term for the W prime. So that's like a lot of mumbo jumbo, but like that was my read of it is, there's a feature map, a new feature map created in the direction of T. There's a difference, a gradient created, and then the gradient helps you update. That was my take.
Yeah, I think the part that was interesting was that they dive into a little bit of this like mumbo jumbo loss function of basically one feature map versus the new, like the new, I don't know if I should call this like P prime or whatever, but like the new spots feature map. And then I think the motion supervision loss here is just trying to get at, it's trying to optimize toward how close is it to T while still maintaining the the discriminative abilities of the next point. And that was like, I think that's what they're trying to optimize for here. That was my read of basically this loss function here. I don't know if that was yours too.
Yeah, no, I think that's a good take on it. And someone had a question on what, any thoughts on applications in 3D space or even higher dimensions? I don't see why we couldn't do this. And, I guess 3D space, the feature maps are based upon a 2D model. So I think, yeah, so the question's like 3D. Well, if there are 3D modeling models, so there could be a question around that. Like, could you use this for those? I think you absolutely could. I think it kind of, like the way this works is it almost moves a model of a 3D object through your 2D image. I mean, that's a little bit of what's happening here. I was thinking more in the lines of like,
I guess I was thinking for like video, let's just say for like video, it's kind of, I mean, even if I think about video, it's like different frames of images that are sped together in a really fast way. And so like the applications for 2D might be more prominent in speeding them and adding them together. You could kind of get to 3D, but I don't know if I don't know if there's a lot of experiments done in the 3D space in image manipulation or in manipulation in general.
yeah, and I think one of my things was one of the things I was thinking is like, okay, well, you can grab two eyelids and make the eye close. Well, do I really even need to specify the points? Could I just say close the eyelids? And that would be more of an understanding of how where do eyelids reside in latent space? What does close mean? Like there's a deeper thing here where you've kind of, you're using a pretty cool technique that works really well, but like, where does this go? Like, if you understood what the latent space was, and could you do it without like the handle points? Like, was one of my like thoughts as I was looking at it.
I think so one of the key lines I just highlighted, thought it'd be worth talking about, was the key idea is that the intermediate features of the generator are very discriminative, such that a simple loss suffices to supervise motion here. And so in here, what I'm thinking about is basically the feature maps, like the intermediate feature maps that it maps to here are so discriminative that a simple loss function suffices to supervise motion. What do you think they mean by are so, like, what do you think they mean by are so discriminative enough?
Yeah, I think what it means is like the features can mean anything, right? They could be like an eyeball, they could be like, they could be features in latent space can mean anything. And your question is like, well, what feature would I edit to move an object, right? Like instead of creating an eyeball, what feature would I edit to actually move it left or move it right? And I think what they're, and then sometimes sometimes that thing might be so complicated, like a simple linear loss, linear subtraction won't minimizing a simple difference between two won't capture the idea of motion. Could it capture the idea of something else? But I think their point was like, there's really simple features here that capture motion. And if you minimize the difference between those and like W and W prime, it would actually capture exactly the motion. So I think that's what it means, but that was kind of my
interpretation. Yeah. I feel like definitely as it got this section, it got really deep in the math. You want to go through a little bit of at least the experiments? We could talk through some of the experiments, or do you want to spend a little bit more time in the actual method itself?
I think there's the point tracking that was pretty interesting, which is the second part, which is like, okay, you've moved W, you've generated a new image. How did you get back your handle?
Yep. Okay, let's go through that part. So in this case here, this is basically after they've gotten W prime. So here, this is where they jump into the nearest neighbor part to actually do, this is post nearest neighbor, where they jump into the actual point tracking. So you guys want to, maybe we could just go through this. So my take from this was at least, so there's okay, zoom out first before we jump into the math here. So I think the thing that my takeaway from this section was that the new point that was actually in W prime, the new point that from the feature map after the loss was done and they got to the new P, what my take was that actually the feature, this was kind of line specifically, we denote the feature of the initial handle point as Fi, which equals F blah, blah. We denote the patch around Pi as whatever this is obtained by searching for the nearest neighbor of Fi in this space over here. My take of this was that it's actually, once it has the feature patch, it then does a nearest neighbor and then identifies using shifted patch loss what the new P point over here should be. So it's almost like it's generated a space of all of the possibilities. So like, should the eyeball be this? Should the eyeball look like this? Like, should the crease be over here? And then it takes just the nearest neighbor to identify what the next handle point should be. And that's kind of how it lands on the next P point. I don't know if that's kind of what you got too.
I think this is good as I feel like it's a good explanation. I feel like this one, I would say I feel like that's a really good explanation. I mean, that's kind of what I think is happening as well. Like, it's a nearest neighbor search to find across the feature map difference to find like the point that matches it closest to.
It's hard because I think there's so many, like, okay, it wasn't totally, until I saw the video, if I just take the line example, it wasn't totally obvious to me that, for example, the jaw would open. Like when they pulled in two separate directions, I thought, well, how are they going to do that? There's like one's moving up and one's moving down. And it wasn't totally obvious to me until I saw the video. Oh, well, if the mouth opens, then you can kind of get up and down. And so the part there that was really interesting was like, well, it did kind of first one P to, I don't know, I'm calling it P prime now. And then the next P, like the jaw P to the jaw P prime. And so it's almost going through it like maybe it's doing it iteratively, and that's kind of how it optimizes. But there's a landscape image where it did all of them all at once. And so there's some like loss function where it's maximizing what's realistic in all of the possible feature spaces. But like, I think that was, do you get that? Do you get kind of what I'm trying to say there?
Yeah, no, I think I do. I mean, I think there's, I think the point tracking approach it sounds like novel as well in this. Like, it sounds like most point tracking doesn't work in kind of, I guess, feature map latent space. It works in some image volume. And again, that's not an area I've ever looked at or thought about much, but it looks like there's a lot of approaches to point tracking. This was like a unique one for using latent space to actually track the point.
Yeah, I think the part that was really, really interesting for me was, well, they're balancing, if you have multiple P's, multiple handle points, you got to optimize so that each of the P's also move towards their target in a realistic way. And you're maintaining kind of nearest neighbor for each one of those P's. And so like these examples here all only show one, but as it got to like an example right here, where there's multiple P's and multiple T's, being able to perform nearest neighbor on all of these P's, and then get to kind of the new point, and how does it optimize that? I mean, that was really, I think, part of what was interesting to me, is like, how is it balancing or optimizing for all of these all at once? Right? Like that, even when you look at it as a single point, it seems a lot easier, but when you're looking at it as multiple points, it looks it's a lot more complicated under the hood. Cool. Anything else you wanted to go through in point tracking?
It was good.
Cool. Okay. I think next we can go through maybe some of the experiments and then talk through some of that in the paper. So they did a couple of different experiments where first they compared against StyleGAN 2, and then they actually compared against, I think, Raft, which was the most kind of, call it state of the art for point tracking. So they compared it to Raft, which is kind of the state of the art in point tracking. And then they compared it against really user control LT, which is kind of the state of the art in manipulation up until that point. But this paper kind of combined point tracking and manipulation together, using that was kind of like the two benchmarks that they used here. And I actually thought it was interesting. Like, this is Raft, for instance, and Raft was going through, and this is an example where they had the input. They're trying to move the lion red point over to the blue point, and comparing basically the approaches here. I mean, it's interesting. Some of these, the lion is like right on top of the blue point. Here, there's kind of a little bit of still misses, or somewhere the scenery was a little bit off still in Raft. And so that was interesting, kind of seeing how their approach, like slight differences between kind of the previous approaches here. And it got it slightly better, I'd say. I couldn't actually tell that much of a difference between pips, but I think that was probably the closest to the new paper here.
Yeah, and I think the point is, like, I don't think those are actually, the manipulation that is just like an image movement, and it's just point tracking, I think, not actually image manipulation. So how well is, point tracking occur?
Yeah.
And then the one on the right is actually the comparable with the manipulation approach.
Yep. Maybe we can talk a little bit about, so the authors afterward had a discussion about what the potential of this might be, obviously some of the social impacts of this, if this type of technology is deployed. Any takeaways for you, Jason, on just applications potential of this?
I mean, it's clear. I don't know if people have been following like Adobe Firefly. I think it's Firefly. Pretty is it? It's pretty amazing. I can imagine tons of stuff in image around I mean, just the flexibility to take a picture and then not get the perfect pose and then edit that pose or change it or and I think the future is also like, you know, not just like point by point picking, but the whole fact that you can manipulate latent space and find features that in this case mean just movement. Like if there's an object and I can move this object and do it. And I see a big future of understanding latent space and doing these manipulations without even handles or different ways of discovering what is what in latent space and making edits on that. And like it just to me was kind of eye-opening on the potential.
Mm-hmm. Mm-hmm. Yep. It was interesting. They mentioned things like out of distribution manipulation. So if you pull things that, so this is examples like up here where it showed some where it's kind of our approach has extrapolation capability for creating images out of the image training, image distribution, extremely open mouth, greatly enlarged field. So it's kind of, I think they were highlighting it can be extrapolated for images not necessarily within the training data set. And then they called out some of the limitations of still things like training data. So being able to give it a variety of, it says handle points in textureless regions sometimes suffer from more drift in tracking. So they were mentioning kind of having texture in the handle points was helpful, but just interesting where this could go as areas for improvement with this paper.
I feel like every week it's there's something that drops that looks like magic. This one definitely felt like magic.
Yep. Cool. Well, I think that was kind of this paper, a lot of depth in this one, but I think I mean, I think the biggest takeaway from this one was being able to actually use point-based tracking to do image manipulation. So identifying a couple points, using that to actually manipulate the image. And I'm curious if this is actually used in something like Adobe or Photoshop or things like that, where you can go pull this, use, this kind of capability becomes easier for like movie editors or things like that. So that will be exciting to see that. Cool. Thanks, y'all. Thanks for joining another paper reading. See ya on the next one. Bye.